Okay, so let me sort of sketch out the proof that we did at the end of class last time. So remember, we're heading towards the Heine Borel theorem, which is tells us about compactness. So let me just sort of set it up here. Heine Borel theorem, and what it tells you about is compactness in Rn. So in Rn, the following are equivalent. Okay, so people will often use this abbreviation. The following are equivalent. One, a set is closed and bounded. Two, a set is compact. And three, a set is limit point compact. Okay, and remember, limit point compact means that whenever you have an infinite subset, then that infinite subset has a limit point within your set, right? So you've got this set, and then you've got an infinite subset in here that's guaranteed to have a limit point inside your original set. Okay. Yeah. Okay. So what we did at the end last time was show that any K cell is compact, right? So all K cells are compact. And we did it in this cool way, where we said, well, suppose you have a K cell, and it's not compact, right? Suppose it's not compact. So you've got this K cell, and it's not compact, and that means that there's a bad. Remember what that means? That means there's a bad cover, right? Right. Being compact means that every cover has a finite subcover. Being not compact means that there's at least one bad cover for which there is no finite subcover, right? So, i.e., there exists a bad cover, G alpha. Okay. Well, if there's this bad cover, then when you divide the intervals that create the K cell and create these sub-K cells, it's like these, we typically call these like the child cells. Okay, so we've got like this parent cell and then the child cells. Well then, there must be at least one of these child cells must not have a finite subcover, right? Because if they all had finite subcovers, then the parent would have a finite subcover, and then this cover would be good, but it's bad. Okay, so you say, okay, well then we can find a child cell, and we call it I1, that for which there is no finite subcover. Okay, and we diagonally divide that guy, we get another child cell, which we call I2, which doesn't have a finite subcover, and so on and so forth, right? So you keep on, you go like this, and you create a sequence of nested K cells, right? And you notice that the diameter, every time you take the child cell, the child's diameter is half that of the parent. Okay, and so then what you do is you say, well, now what we're going to do is take the intersection of all those guys, right? The thing that we showed just before was that if you have nested intervals or nested K cells, which it could be extended to K cells, if you have nested K cells, then the intersection is non-empty, right? The intersection is non-empty, and so we know that we take the intersection of all these guys, right? We know it's not empty, so it contains some point x star, right? Some x star. Okay. Okay, but x star lies in the original parent cell, so x star is contained in some G alpha naught, right? From the bad cover, right? There's somebody from the bad cover that covers that point, right? Okay. G alpha naught is open, is open. And so that tells you that x star lies in some interval. I'm sorry, in some neighborhood that lies inside of G alpha 9. We're just sketching over the proof we did at the end last time. Okay, right? So we know that this x star here has a definite radius around it that's contained inside of the G alpha. Okay, okay. But now choose n big enough, large enough that the diameter of isoben is smaller than the radius of that neighborhood, right? Okay, so this x, right? The isobens are shrinking by half in diameter every single time. So eventually, we can get one that's smaller in radius than this radius, smaller in diameter than this radius, right? But that tells us that the isoben, right, lies entirely inside of the neighborhood, right? Because the diameter is smaller than the radius here, right? Okay. Or I can make it like even more explicitly so, right? So let's say that the diameter of this guy is smaller than half the radius, right? So then, at the worst, we're going to touch the edge here, right? At the worst, we're going to touch the edge. Okay. But in any case, we lie inside this guy. But then what happens? Then that's contradiction, right? Because the isoben, so isoben is covered by G alpha naught, but our isobens were were constructed so that none of them had a finite subcover, right? None of them were finitely covered by the G alpha, but we've just created one G alpha that covers isoben, right? We found an isoben that's so small that it's contained inside this single G alpha naught, and that's a contradiction. Okay. Okay. So all K cells are compact. Okay. Any questions about that? Okay. This is a kind of a cool idea. Yeah. Yeah. This is. I think this was used in a science fiction story by Piers Anthony many years ago. I don't know if you know the author Piers Anthony. He's not popular anymore, I think. But in one story, the main character is trying to capture this horse, and he has an infinite. The horse is wandering on an infinite plane, and he has this ball of string, and he rolls the ball of string across and cuts. I guess he rolls it in both directions or something like that. Anyway, so the horse can't cross the string, so he traps the horse on one side of the line, and then he rolls it and then traps the horse on the other side of the line, and then keeps on going farther in and eventually captures the horse. For your amusement, there's an article on the mathematics. It's sort of like a joke article on the mathematics of big game hunting. And the author is H. Petard. It's a bunch of just like how you might catch a lion, using mathematical ideas. This is not a real name. It's from Hamlet, where Hamlet says that Rosencrantz and Guildenstern are hoisted by their own petard, right? They got captured by their own trap, basically. Okay, enough of that. Okay, so all K cells are compact. So now we've got basically almost all the components we need to prove the Heine Borel theorem. So Heine Borel is really nice because what it says is that in Rn, compactness is very simple, right? If you want to check a set is compact, you just need to check if it's closed and bounded, right? So previously, if you wanted to check is compact, you have to say every open cover has a finite subcover, right? But this is a far easier condition to check. You just check what's closed, check what's bounded. Okay, so let's take a look at it. We're saying that all of these statements are equivalent to each other. Okay, so what we're going to do, the strategy, the plan is to prove that A implies B, B implies C, and C implies A. Okay, so everything will be equivalent to the other, right? You can get from any one statement to any other statement. So proof of A implies B. Set is closed and bounded implies that it's compact. Well, if F in Rn is closed and bounded, I guess we don't need the bounded. If it's bounded, then it's contained in a K cell. Right? F is contained in some K cell. Right? You can just, it's bounded, so it's, you can find some just choose some K cell big enough that contains it. Okay. Why is it compact then? Then it's compact. Why? Talk to each other for a minute. Don't say anything. Talk to each other for a minute. Walk outside.
There's a room that says closed subsets of
Yeah. There is the room. So, at least 30.
I don't know the number.
Okay, so why? Why is it compact? You've got this set. It's sitting inside of a K cell. We know that K cells are compact, right? And we know that the set is closed, right? You have a closed subset of a compact set. We showed that any such set is compact, right? Do you remember? You take, whenever you've got an open cover, you extend it to the cover of the big guy, and then you throw out the F complement at the end, right? Okay, so right, F closed in compact set implies F is compact. So that's easy. B implies C. Set compact implies that set is limit point compact. We did that already, right? That we did last time, right? So done already. Okay. So the only thing we have left is to show that C implies A, right? That if you're limit point compact, then you must be closed and you must be bounded. Okay. So okay. So we want to show that the set. So say E is a subset of Rn, and it's limit point compact. Okay, we want to show that E is closed and B is bounded. So let's first do closed and bounded. So step one, show that E is bounded. Okay, so you say, well, look, if E is not bounded, right? If E is not bounded, that means that it's not contained in any ball. Okay, so that means that if we consider like if we consider any ball of radius n, say like for n in the natural numbers. Okay, if we consider any ball centered at the origin of radius n, that does not contain E, right? E cannot be contained in there. Right? E is not contained inside of any ball centered at the origin, right? Because if it were, it would be bounded. Okay, so for each n, choose a point, E sub n, that lies outside of that ball, but in E. Right? So you just take the origin here and you create a series of balls of integral radii, right? And then you know that that E is not contained in any one of them, right? So you can choose a point of E that's not in the first ball, call that one E1. You can choose a point of E that's not in the second ball, call that E2. Choose a point of E that's not in the third ball, call that E3, and so on and so forth. Okay. Well, the sequence E sub n, if we look at the collection of all those points, right? This thing has no limit point. This thing has no limit point in E, right? It has no limit point in E because the points are heading off towards infinity, right? And so they can't accumulate. They can't accumulate, right? Remember, right? To be a limit point means that every punctured neighborhood has infinitely points of E inside there, right? But I'm sorry, infinitely many points of the E sub n inside there. But there are no such balls, right? There are no such points, right? Because the points are heading off towards infinity. So E could, So E must be bounded. Okay. Now the second part is to show that that E is closed. Okay, so step 2. So second, I should call this like claim 1, E is bounded. Claim 2, E is closed. Okay, let me make sure I'm saying this right. Yeah, okay. Okay, so suppose E is not closed. Okay. Suppose E is not closed. Well, that means that there exists some point, I'm calling it, x naught. There exists some point x naught in the complement of E that such that x naught is a limit point, right? Right. So there's some limit point, right? But it's not in E, right? So the set is not closed. It doesn't contain all its limit points, right? Okay. So there's this limit point that's not contained in E, x naught, and what we do is we take radii of 1 over n. Okay, so we know, since it's a limit point, we know that there's somebody in here. In each radius of radius 1 over n, there's some point of E, which we'll call E sub n. Okay, so choose E sub n that lie in the punctured neighborhood of radius 1 over n around x naught. So for n going from 1 to infinity. Okay. Okay. So this is an infinite, right? choose E sub n lying in E intersect that. Right? We know that there's somebody in there, right? Because x naught is a limit point. Everybody okay? Yeah. Following? Okay. Right. So, okay. So now, what are we going to say? This is an infinite, right? E sub n is an infinite subset of E, right? And right, we know that our space is limit point compact, right? Okay, so we want to show that E limit point compact implies that it's closed and bounded. So we're trying to show that it implies closeness, right? Right. So it's an infinite subset of E, right? And so it has a limit point. Right. Clearly, x naught is a limit point of x naught is a limit point of the E sub n, right? And so by limit point compactness, you know that that x naught must lie in E. Okay. So I'm cheating a little bit actually. This is not. We're not quite done actually. Okay. So let me sketch out what we're doing. Okay. So we're trying to show that limit point compactness implies the guy is closed. We say suppose it's not closed. Then there's this guy in the complement there's a guy in the complement who is a limit point of E, right? We construct an infinite subset of E, right? We construct an infinite subset of E. By limit point compactness, we know that this thing has a limit point. Okay, this thing has a limit point, and we say that limit point must be x naught. Okay, and because it must be, so we'll fix this in a second. Why must it be x naught? But if x naught is the only limit point of this set of this set, then it must lie in E because E was limit point compact, right? So E was limit point compact. We constructed an infinite subset of E, and we say that x naught x naught is the only limit point of this, and so x naught must lie in E. Okay, so contradiction. Okay, now why must x naught be? Why can't there be any other x? Why can't there be any other limit point? Why is x naught the only possible limit point of the E sub n's? Okay. Well, suppose there's another one. Suppose y is also a limit point, is another limit point of the E sub n's. Okay. Okay. So now, so in that case, we'd have x naught, and we have y, and we have the E sub n's, but the E sub n's should be getting infinitely close to both of these guys, right? So we have the E sub n's. Okay. Now look, the distance between x and y is controlled by the distance between x naught and E sub n, and E sub n and y, right, by the triangle inequality. right? Now, yeah, let's do it this way. So now, let's move this thing to the left-hand side. X naught minus y minus x naught minus e sub n must be less than e naught minus y. Right? So I'm just moving this thing over the left-hand side, right? Now, as e sub n, as n gets really large, the e sub n get infinitely close to x naught, right? That's how we constructed them, right? The distance is 1 over n, right? So now for n large enough, the distance from x naught to n is smaller than a half of the distance between x naught and y. All right, so choose n big enough. Choose n big enough that the e sub n's have gotten more than the distance to x naught is more than is less is less than half the distance of x naught to y. Okay, so then in that case, what we have is that the distance from en to y is bigger than half the distance from x naught to y, right? Because we have x naught, the distance from x naught to y, minus something smaller than half that distance, right? So what we have left is greater than half that distance, right? Okay, right. But that means that after a certain point, the ENs are going to stay away from y, right? The ENs, you know, are not in this neighborhood, right? So then En would not. I'm sorry. So then y is not a limit point, right? So y cannot be a limit point. Of these things. So what does it tell you? That tells you that x naught is the only limit point, and by limit point compactness, it must lie in the set. And so so x naught lies in okay, contradiction. We said x naught was an E complement. Okay. Does that make sense? Do you guys have questions about that? Should I say it again? Do you want me to say it again? EIN.
The idea of clustering around X seems important. Is that kind of an important idea for like all limit points, or is that kind of just a result of how we constructed the neighborhoods around X naught?
Yeah, I mean, this is a little bit special because our E sub n's are constructed to go to x naught, right? So for a general limit point, all you know is that every punctured neighborhood has infinitely many points in there. But you don't know anything about, it's not a sort of a sequence thing. It's rather just a set thing,
Okay.
right? There's infinitely many points in here, but in this case, we're actually constructing a sequence, and that sequence goes, that sequence gets progressively closer to x naught.
Okay.
Okay, so yeah. Okay, so that's it. Yeah, that's the proof of the Heine Borel theorem. Okay, so that's kind of the climax of all your knowledge on compactness. Okay, so yeah. Okay. And like I said earlier, what we'll see in the next chapter, actually, I should say after this chapter, we're going to jump to chapter 4, because it kind of makes more sense to do that. I've always done it that way. So we're going to jump to chapter 4, where we'll see how these results on compactness can be used to prove theorems about continuity and stuff, right? The stuff in calculus that was left unproven. Okay. I guess I do it this way because otherwise, we'll get into the weeds of chapter 3, which is about sequences and series. And by the time you get to chapter 4, you'll probably have forgotten everything you knew about compactness. So we're going to do, we'll do those results first, and then we'll come back and talk about sequences and series of points. Yeah, so we'll do continuity, we'll do differentiation, and then come back to sequences and series. And then the last thing we'll do in the course is sequence and series of functions, right? Instead of considering points, well, it's basically like, you think of points as these things inside of a metric space, but you could also think of them, you could also consider the set of all functions, and then consider the set of all functions, and then put a metric on that space, right? Could put a metric, some sort of distance between functions on that space. In that case, your functions are the points, right? And you can talk about sequences of points, but now the points are functions, right? And you have functions that converge with respect to some metric. Okay. So that's the power of this theory, and why it's not just a thing about Rn, but about metric spaces in general, right? Because the space of functions can be made into a metric space. I mean, we'll make that precise. Okay. So there's only one more thing I want to cover in this chapter, and that's the notion of connected sets, okay, which we use almost not at all in this course, I have to say. But it is something that you'll see a lot of if you take a course in complex analysis. So complex analysis is kind of like a successor to this course. Except in some sense it's much easier. Like the results in complex analysis happen with a lot less effort than like the results. You get very miraculous results and without much effort. They work out really nicely in if you're talking about differentiable functions on the complex plane. That's kind of considered one of the cutest courses in mathematics, I'd say, because everything works out really, really beautifully. Yeah. Okay, so we're not going to really talk about connected sets here, but let me just at least introduce the idea. Okay. So here's the definition. As usual, you have some metric space, and you have some. We have to sort of, the definition is a little bit kooky, but you have some two sets inside the metric space. Okay, and so here's sort of the initial definition. If A closure intersect B is empty, and A intersect B closure is empty, then we say A and B are separated. Okay, are separated. Okay, so if you're in R1, for example, and you have these two intervals, A, B, and then B, C, right? Then you see that the closure of, so this is A, my A, and this is my B. A closure doesn't intersect B, and B closure doesn't intersect A, right? And these are separated sets, right? Or more obviously, if we took things that were intervals that were some distance apart, the closure of this guy doesn't intersect that guy, the closure of that guy doesn't intersect this guy, right? But they could be right up next to each other as well. Okay. So that's what separated means. Okay. And then we say if let's do it this way. If E can be expressed as a union B, where A and B are separated, then we say E is disconnected. E is disconnected. Okay. So like if I had you know 0, 1 union 1, 2, well that would be that's exactly this sort of thing. It's expressible as a separated set, right? You can express it as this union this, and those are separated sets, right? So then E is disconnected. Okay. So whenever you can express it as separated sets, then it's just disconnected. If E cannot be expressed as a union of separated sets, then we say E is connected. We say E is connected. Okay. Right. So so for example, if we took the interval 0, 2, there's actually no way to express that as separated sets. Okay, there's no way to do it, and no matter what you try, like if I took, say, maybe the obvious thing is to do something like that, right? I'm going to split it into this and that, but then the closure of this guy would intersect this guy, right? Right. If I call this guy A, if I call 0, 1 A, and I call 1, 2 B, right? You see that that's not a separation, right? Because this closure intersects that guy. Okay. So yeah. Notice that if you're separated, then you're definitely disjoint, right? So separated. So remark. Separated definitely implies disjoint, right? Because you intersect the other guy's closure is empty, right? You intersect the other guy is empty, right? So they're disjoint. One notation that I occasionally use is this. So people use this to indicate a disjoint union. Okay. So if you see me write like this, it means like E is a disjoint union of these two sets. That it's the union, and these guys are disjoint from each other. Right. So I could have written it here because A and B are separated, so these guys are disjoint. Okay. Okay. I should say that if we're in higher dimensions, there's another notion called path connected. Okay, there's another notion called path connected, which you'll see in complex analysis if you take it. And what that means is that you have a set, and every pair of points can be joined by a path that lies within the set. So there's every point is path connected to every other point. Okay, so like something like this, of course, would not be path connected, right? Because I can't get from this point to that point, right, without leaving the set. Okay, but we're not even going to talk about that here. Okay, so the theorem, the only theorem we're going to give is the following: that a set in R1 is connected if and only if for all x and y in E, the entire interval xy is contained in E. Okay. The entire interval is contained in E. This is, or I could say, yeah, of course, I can close that since x and y are in E. Right. Okay, so this is sometimes abbreviated that E is a linear continuum. Okay, so what it says is that connected means that whenever you have any 2 points inside of E, then everything between them is also inside of E. Okay, this is actually the same thing as saying it's path connected. Okay, right, so this is equivalent to saying E is path connected. It's not true in general that connected means path connected, but in the case of R1 it is true. So, okay, got 10 minutes, not sure we can do it. It's a little bit complicated, but not that complicated. Okay, so what we're gonna do is prove by contraposition. So proof by contraposition to show that A implies B. We're going to show that not B implies not A, right? So we'll show that if E is not a linear continuum, then E is not connected. E is disconnected. Okay. So suppose E is not a continuum, right? In other words, suppose there exists some x and y in E where this whole interval is not contained in E, right? In other words, there's some point, i.e., there exists some point z in the interval such that z is not in E. Okay. So we've got our E. We've got these 2 points, x and y. They're both in E, but there's this point between them that's not in E. Okay. And we're going to show that E is disconnected. And it's kind of obvious how we're going to do it. We're just going to say, well, take let A sub z equal E intersect negative infinity z, and let B sub z indicate E intersect z to positive infinity. Right? We kind of do the obvious thing. We say, let A sub b be everything to the left, let B sub z be everything to the right, and that gives us our separation. Right? Because the closure of the stuff on the left doesn't intersect the stuff on the right, and the closure of the stuff on the right doesn't intersect the stuff on the left. Right? Because when you close it, at most you're going to get this z, but z is not in E. Right? Z is not in E, and so we don't have to worry. We're not going to intersect B sub z, right? So when we close the stuff on the left, at most we're going to add on this z, but still we're not going to intersect the stuff to the right of z, right? And vice versa. Okay. So that's the easy direction. Okay. The harder direction is the reverse, and it's not too bad. Again, we'll do it by contraposition. So we're trying to show B implies A. We'll show that not A implies not B. So we'll show that if E is separated, right? If E is disconnected, then E is not a linear continuum. Okay, so here's how we're going to do it. We say, suppose, as usual, suppose E is disconnected, right? So suppose E is the union of two two sets where A and B are separated. Okay. Okay. So. Okay. So E is expressible as some union of some guys A and B, and there may be, B could have some stuff on the left here, and A could have some stuff on the right. It's not, it's not so left-right split like we in the previous case. Okay. So we've separated into these two separate sets. Okay. Pick any point in A and any point in B. Okay. And without loss of generality, assume A is less than B. Right? It doesn't matter. I mean, if it's the opposite way, we can just relabel everything and then call those guys the B's and those guys the A's. Okay. So now we want to show that E is not a linear continuum. So what we're going to do is basically try to find a point that right. We want to find a point that sort of lies in between these two guys, but is not in our set, right? For it to be a continuum, right? We've got A and B. Everything in between should be in our set. What we're looking for is a point that doesn't lie in our set. Okay. So here's how we do it. We say, well, let Z denote the supremum of A intersect the interval AB. Okay. So we take the interval AB, and then we intersect it with A. Okay. Right. We intersect it with A. It's got some point in there, right? And we take the supremum of everything that's in A inside there. Okay. Okay. Notice that this thing is the supremum of this set, which means that it's contained in the closure, right? Which means that it's contained in the closure of the set, right? Which is contained in the closure of A. Right? But remember, A bar intersect B is empty. Right? So observe that Z is not in B, right? Because Z lies in A bar, and A bar intersect B is empty. Okay. So Z bar is not in B. In particular, Z bar cannot be equal to B, right? It's definitely not this endpoint here because that's in B. In particular, Z is not equal to B. Okay. So now we say, well, look. Suppose there's two cases. Case one. Suppose Z is not in A. Okay. There'll be two cases. Z is not in A, and Z is in A. Okay. So suppose Z is not in A. If Z is not in A, and it's not in B, well then we're done, right? Because E was the union of A and B, right? In that case, Z does not lie in A or B, but that was E, right? And we found the point that lies between A and B and is not in our set, right? We found the point that breaks the continuum. Okay, so that's easy. Case two, say that Z actually is in A, right? Okay. Right, okay, yeah. In that case, right, since A intersect B, B closure was empty, we know that Z is not a limit point. So Z is not a limit point of B, right? right? Because it's not, it's in A, but A intersect the closure of B is empty. So B is not a limit point. B is not a limit point of B. I said Z is not a limit point of B. Okay. Not being a limit point, well, what does that tell you? So here's Z, here is X, and here is Y. No, what am I calling them? A and B. Here, A and B, right? Not being a limit point means that, that we can find a neighborhood around it, right? So we can find a neighborhood around it that doesn't intersect B, right? So there exists a neighborhood around Z, a punctured neighborhood such that the punctured neighborhood intersect B is empty. Okay. So there's nobody from B inside here. There's nobody from B inside here. Okay. Right. And we can choose it small enough that it's inside this neighborhood. Okay. So now just take a point inside. Take a point to the right of Z. Pick Z1 inside that neighborhood. Where Z1 is bigger than Z. Okay. So then this Z1 is not in B, right? Z1 is not in B, right? And Z1 can't be in A, right? Can't be in A because Z was the supremum. Z was the supremum of everybody in A that's inside this interval, right? And Z1 is bigger than that, right? So Z1 is not in B and Z1 is not in A. And again, we found the point that breaks the continuum. Okay. So this is the key point here, right? If it's disconnected, you've got these two sets. Choose 2 points inside the sets. Choose 2 points inside the sets, and then take the supremum. Look at this interval AB, and look at the supremum of everything in A inside there. That's basically, the key point. That's how you're going to find the breaking point. Okay, that's it for today. Okay.